Okay, the first classic example is called time dilation. Time is a relative quantity, believe it or not. Let's look at this experiment. I have a spaceship that's flying with a speed v forward, okay, with a speed v forward. And inside that spaceship, an astronaut plays a game. He shoots a beam of light, okay, shoots a beam of light perpendicularly from the direction of movement. So the spaceship moves in the x direction with the speed v, and it shoots a beam in the y direction, and it travels from the bottom of the ship to the ceiling with a distance d, okay, with a distance d. So that distance from here there is d, and then beam of light comes back. So the total distance it traveled is 2d, up and down, 2d. And he wishes to find how long would it take for the beam to go this way and back. Now that's very, very easy to do because the distance is 2d, right? The distance is 2d and the speed of the beam going up and down in both cases is c. Okay, I'm going to ignore the speed, the difference in speed of light in vacuum and the speed of light in air because they're almost the same. So it's it's c. All right, so that is the time it takes for the beam to go this way and that way. We call it delta t. Okay. As a matter of fact, we're going to add a little subscript p here for this particular time interval. P, what does p mean? P stands for proper. This is a time interval between two events. One is the emission of this beam, and secondly is the reception of this beam, right? The time interval is delta t. Why do we call it proper time interval? What does proper mean here? Proper means these two events, the emission of the beam and the reception of the beam, took place at the same location. Okay, according to the astronaut, you know, the beam started here and ended up there, right? Same location. When you measure the time interval between two events, and if these two events took place at the same location according to you, then the time interval you measured is called proper time interval. That's what P means. Okay, now let's look at the same event that from a different point of view, from the Earth-bound observer's point of view. To the person on Earth, the spaceship moves forward. Okay, so the beam did not quite travel like this. Rather, it moved up the ceiling. At the same time, it also moved along the direction of propagation, of movement of the space shuttle. So by the time the beam reaches the ceiling, the space shuttle is no longer here. Rather, it is there. So the beam, on its way up, traveled a path like this. All right. And then as the beam comes down, the spaceship is already there, and therefore on the way down the beam traveled like that. Okay. So you see, according to the Earth-bound observer, this beam traveled a longer path than that path, right? And if you use classical physics, that's understandable because even though it travels a longer path, it also had a greater speed, okay? Because it's riding, you know, the beam of light is riding on a moving space shuttle. But remember, relativity says, if you measure the speed of light, what are you going to get? You always get the same value, c, no matter what. Whether it's this observer, s prime, or that observer, s. Either way, it's going to be the same speed, c. You're stuck with that same speed, c. Okay, same speed, but greater distance of propagation. What does that tell us? It must have taken longer time for the Earth-bound observer S to view this event. Okay, so it starts and ends, the time interval delta t must be longer than delta tp. Okay, again, the time interval between two events, the time interval has different values depending on who's measuring it, and clearly that is because we have to insist on using the same speed of light in both reference frames. Now, how long is this delta t going from here back to there? This is easy to calculate. Okay, so the beam starts out from here, goes this way, and comes back. The total time it takes to go up and down is delta t. And because of the symmetry, it takes half the delta t go up, half the delta t to go down. Now, the beam travels with the speed of light c. So the total distance from here to there is c times the time, which is delta t over 2. And then again, c times delta t over 2 coming back. Meanwhile, the spaceship traveled from here to there with a speed v. Same time interval delta t over 2. So this distance is v delta t over 2. Okay, and that, of course, is the distance between the floor and the ceiling of the space shuttle, and that's d. You look at this right-angled triangle here, very simple mathematics, okay, a Pythagorean theorem, high school stuff. You'll find that this thing squared equals d squared plus that thing squared, which is right here. And then what happens when you solve for delta t? Unbelievable. When you solve for delta t, you're going to find delta t equal to 2d over c divided by square root of 1 minus v squared over c squared. Now we know what that is on the top. That's 2d over c. That is delta t proper, right? This is the time interval measured by the astronaut. And you divide this by this factor here. This factor, 1 minus v squared over c squared. It's going to appear very often in relativity, and we give it a name. Okay? We define gamma as 1 over the square root of v squared over c squared. Gamma is always greater or equal to 1, okay? Because the denominator is less than 1, the numerator equals 1. And therefore, delta t is greater or equal to delta tp. In other words, the same time interval measured by the astronaut is always going to be shorter than the time interval measured by any other person who is moving relative to the space shuttle. Okay, this and the difference is a factor of gamma. Okay, so this is equal to gamma delta t proper. Delta t equals gamma times. So the time interval measured by anybody else instead of the person who is relatively at rest with the two events is amplified by the factor gamma. And here's what gamma is. Now this is stunning because we've never had this experience before, and that is different people will have a different time measurement. You always thought time was absolute, right? But no, time is not absolute. The Earthbound observer has to observe a longer time interval. It's very simple because he sees the same beam of light traveling a longer distance with the same speed. Of course, it took longer time to do that. There's no question about this. Okay, and again, you can see here this new stunning result that time can be twisted. Really is a necessary result. Okay, from the constancy of the speed of light. This gamma factor is greater or equal to 1, and usually it's pretty close to 1 actually. Because v is usually a lot less than c. Even if you lose the speed of light for v, speed of sound for v. Okay, speed of sound is how much? Is a few hundred meters per second, but speed of light is 300 million meters per second. So v over c would be 1 in a million. Squared is even smaller, so this is negligibly small, this factor here. So gamma is almost equal to 1. Therefore, when gamma is almost equal to 1, even up to the speed of sound, you find that delta t and delta t proper, there is virtually no difference. You cannot measure that difference unless you have a very, very accurate clock. Okay, therefore, this time dilation thing has eluded our observation for all this time until Einstein discovered it. Why do we call it time dilation? What does dilation mean? Dilation means the same delta t proper measured from another person's view is longer. So time has dilated, has expanded. It's like an elastic band. Okay, this does not only apply to the beam of light going back and forth. It applies to any event. For example, an astronaut, let's say he has a heartbeat of 60 per minute. Okay, so the time interval between two heartbeats, according to himself, is 1 second. That is delta t proper because the two events, the first heartbeat and the second heartbeat, took place at the same location according to himself, both on his own body. Okay, so the time interval 1 second is the proper time interval. But according to an Earthbound observer who has a telescope trained on that fast-moving space shuttle, the same heartbeat interval between the two heartbeats is gamma times delta TP. And depending how fast V is, gamma can be significantly greater than 1. We can look at some numerical values, okay? Here's a plot from the textbook, the value of gamma. You know, V equals whatever value, and that will determine what gamma is. What this is V measured in the units of 10 to the 8 meters per second. So you may not be able to see it clearly. This is 0, this is 0.5. The 0.5 means 0.5 times 10 to the 8 meters per second. This is 1 times 10 to the 8 meters per second. That will be 1/3 the speed of light. And when it's equal to 3 times 10 to the 8 meters per second, you're getting the speed of light. Okay, now this gamma factor initially is very close to 1. So you have very little time dilation effect, and gradually it picks up and it goes dramatically up. In fact, when V equals C, what is gamma equal to? Okay, look. When V equals C, V over C approaches 1, therefore 1 minus 1 approaches 0. You have a 0 in the denominator, and therefore gamma approaches infinity. Okay, in fact, worse yet, when V is greater than C, you're going to have a negative value overall under the square root. So gamma would be imaginary. So therefore time measurement will be imaginary. And what does that mean? It doesn't mean anything. Physically invalid. And therefore, because of this gamma factor, we have one important conclusion, perhaps even more famous than Einstein's second postulate to the average person, and that is the speed of light is the fastest possible speed in the universe. Okay, I must tell you, as you can see here, the speed of light being the fastest speed, it is not a postulate of Einstein's. It is something we can derive from his postulates. Okay, we never said to begin with the speed of light has to be the fastest speed. We just said it has to be universal speed, that's all. But it turns out, because it's a universal speed, it also has to be at the same time the fastest speed possible, because otherwise you would have a negative value inside the square root for gamma. You could get imaginary time, which is physically invalid. Okay, and if you look at some numerical values, for example, if the speed of light, if V equals, say, 80% of the speed of light, okay, 80% of the speed of light. So what are we looking at? We're looking at V over C equals 0.8. Okay, so gamma equals 1 over the square root of V over C, which is 0.8 squared. 0.8 squared is 0.64, so 1 minus 0.64 is 0.36, which is a perfect square. This is 1 over 0.6. Okay, so this I can write as 5 over 3. Okay, gamma is 5 over 3. And therefore, if the time interval was 1 second between two heartbeats according to the astronaut, it's going to be 1 second times 5 over 3. It is almost 2 seconds. So therefore, according to the Earthbound observer, if he looks at the astronaut, everything he does through the telescope, he finds that his heartbeat slows down, okay? Instead of 1 beat per second, it is now 5 over 3 seconds per beat. In other words, the heart rate is almost only half as much. Everything slows down. His heartbeat slows down, not just his heartbeat. If he looks at a clock hanging on the wall of the space shuttle, he found this clock also moves slower. The astronaut moves slower. Everything moves slower, except for a beam of light, okay? Everything is slower. This is called time dilation. Now you may wonder, is this a real physical effect, time dilation? In other words, does the astronaut feel that his heartbeat slows down so that he feels suffocating and so forth? Is that true? Does he feel any difference? Absolutely not. Okay, if he can feel any difference, that is a direct violation of Einstein's principle of relativity, because he would say, oh, you know, guess what? I must be moving at a very high speed because I detect my heartbeat slows down. Usually it's 1 beat per second. Now it's half a beat per second, so I must be traveling at extremely high speed. He would have then used whatever information he could gather to figure out his absolute speed, which is, impossible. Okay? All reference frames will yield the same exact physics. So he would not see any difference. He would just behave normally. He would still have a heartbeat of 1 per second, and his clock on the wall, according to him, is still giving him the correct time, except for us. When we try to look at everything happening on the spaceship through our telescope, it appears to us that everything is slowing down except the speed of light. Okay, so that is the famous first example of time dilation. The next important example of the application of special relativity is the so-called length contraction. We already learned that time is no longer an absolute quantity, but what about space? What about the measurement of length? The separation between two locations. Well, let's look at this example. Suppose I have a spaceship that travels from the Earth to another planet, assuming that this planet is at rest relative to the Earth. Okay, now if I measure the distance between the Earth and that planet, and I find that distance to be LP, here P means proper, just like proper time, I have what's called proper length. When is a length measurement considered a proper measurement? So I get what's called proper length. Well, this is the measurement of length when you are measuring a stationary object, which means the object being measured is not moving relative to you, okay? You're measuring an animal when it's not moving, instead of a swimming fish, for example. Okay, so you find this measurement length, the so-called proper length, to be LP. Now, a spaceship travels from the Earth to that planet with a speed v, okay? And the first question is very simple. How long would it take, according to the Earthbound observer, how long would it take for the spaceship to go from here to there? That's easy to do because I have the length and I have the speed, and therefore I find delta t to be equal to LP over v, right? It's very simple. But the question I have now is, what about the same event as measured from the astronaut's point of view? The astronaut, from his point of view, he sees himself moving. He sees this planet, this green planet, moving towards him at the speed v, right? He closes in on him. By the time the green planet reaches his spaceship, he actually has arrived at the spaceship. What is the time interval for that? Okay, so we're looking for delta t measured from the astronaut's point of view. For the astronauts, from the astronaut's point of view, when he starts, he's at a spaceship. When the planet closes in on him, he's also at the spaceship. So these two events, the starting and the ending point of his trip, happened at the same location, which is his spaceship. And therefore, the time delta t in between these two events is actually, by definition, the proper time. Okay? And the proper time, delta tp, is not the same as delta t. We learned just in the first example, it is actually delta t over gamma. Gamma is a factor greater than 1. Okay, in fact, we can calculate gamma if we have some actual numbers. Let's assume that the distance, the proper length between these two planets, LP, is 8 light years. Okay, we also assume that V is equal to 0.8 c. Okay, and therefore, clearly, delta t, the time it takes for him to go from here to there, according to the Earthbound observer, is 8 light years divided by 0.8 c, and that is 10 years. Okay, that's 10 years. Now, meanwhile, we can calculate gamma. Gamma is equal to 1 divided by the square root of 1 minus 0.8 squared, and we learned, we did that same example for it's 5 over 3. Okay, and therefore, delta Tp, the proper time interval, according to the astronaut, between this event and that event, is equal to delta T over gamma, and that is 10 years times 3 over 5, and that's 6 years. Okay, so according to the astronaut, it took him 6 years to go from the Earth to the planet. Now, if he believes that the distance between the Earth and the planet is 10 light years. In other words, he believes the distance is the same, whether he measures it or whether the earthbound person measures it. Then how fast do you think, according to him, the planet must be moving towards him? Well, the planet covered 10 light years in only 6 years. And therefore, the speed of that planet must be distance over time, which is 10 light years divided by 6 years. Whoops, we have a problem, don't we? Because v would be equal to 10 light years over 6 years, and it's greater than c. How is that possible? Something is wrong. So what is wrong? Well, clearly, that delta Tp being 6 years, that is true because that's time dilation we just learned before. And so what is the hole in the argument? The hole in the argument is, according to the astronaut, the distance between the Earth and the planet cannot possibly be that long, 10 light years. Must be shorter than that, which allows the planet, the green planet, to close in on him within a mere 6 years. Okay, so the question now is, how long is the separation between the planet Earth and this green planet according to the astronaut? Okay, according to the astronaut. Well, according to the astronaut, the green planet moves towards him with a speed v, and it covers a distance, whatever that distance L is, with a speed v over a time delta Tp. Okay, so distance equals speed times delta Tp, not delta T. And that equals to v times, what's delta Tp? Delta Tp is delta T over gamma, as we know, right here. And you notice that I have v delta T here. V delta T is just the proper length Lp. Okay, and you divide this by gamma, and I find, let me highlight this, okay, I find that the length separating the two planets as measured by the moving observer, the astronaut, is not the same as the proper length measured. In fact, it is proper length divided by gamma, which is less than the proper length. In other words, according to the moving observer, the length seems to have contracted, has shrunk by a factor of gamma. This is what's called length contraction. So you see, length contraction really is related to time dilation because we use this formula delta Tp equals delta T over gamma, which is time dilation. And the reason why they're related is because both of these effects, length contraction and time dilation, they both come from the very same origin. What is that? And that is the second postulate of Einstein, which is the constancy of the speed of light, regardless of who is observing it, whether the observer is the earthbound person or is the astronaut. The same origin leads to both of these stunning results. All right, we had a lot of fun twisting the notion of space and time. Now let's continue this game, okay? Let's look at the issue of simultaneity. If two things happen at the same time, we say they are simultaneous. Now the question is, if a reference frame, in a reference frame S, an observer sees two things happen simultaneously, will another observer in a different reference frame get the same conclusion that is these two things happened simultaneously? Well, in classical physics, certainly that is true. Simultaneity was absolute. It doesn't depend on who is measuring it. But in relativity, it turns out that is relative as well. Okay, you look at this experiment. Suppose there's a moving car. Okay, a moving car. And there's an observer O standing by the side of the car, and there's another observer O prime who is midway between these two ends of the car. Now, according to observer O, a lightning struck the back of the car at the same time. Another lightning struck the other end while the car is moving forward. Okay, so according to the observer O, who stands by the side of the track, those two lightning struck happened simultaneously. Now, what about O prime? Will O prime, the observer at O prime, agree that these two events took place simultaneously? Well, not so fast. Okay, because it takes time for this beam to travel from here to there before this observer can see it, right? Before this observer can see it. Now, let's say it took a certain time delta t for the beam to arrive from here to there. During the time delta t, what happened to the car? It has moved. Okay, so O prime is no longer here, but it's somewhere there, right? Somewhere there. And therefore, this beam had to travel all the way, not to here, but all the way from here to there to reach O prime. And meanwhile, this beam had to travel only a shorter distance from here to there, right? So, O prime will not conclude that these two events took place simultaneously. Rather, he would have seen the flash from B prime first before he sees the flash from A prime. Now, from his point of view, he was always in the middle of the car, exactly the same distance between A prime and B prime. And yet somehow, he received this flash first and that flash second. Now remember, according to him, the speed of light, whether it's from this beam or that beam, is the same. It's c, okay? And therefore, he says, okay, same speed and same distance to travel, and yet you arrived first. So guess what? You must have happened first. So B prime happened first before A prime. Okay, so he does not agree that these two events took place simultaneously. Rather, he said this happened first, this happened the next. So simultaneity is also a relative quantity. If one agrees it's simultaneous, another person in a different frame may not say it's simultaneous. Okay, the stuff we've been talking about, they're quite mind-boggling, right? And you might think that these things are just, you know, in your mind, in your dreams. Do they have any real-life consequences? Have we been able to verify those stunning time dilation and length contraction events? Well, it turns out, yes, we have. Okay, when it comes to time dilation or length contraction, there's a very famous experiment called muon decays. Muons are unstable particles. They're like electrons because they're charged, but they are about 207 times heavier than an electron. It doesn't really matter that much. We have muons created from cosmic radiation, so we get muons flying from outer space, basically, and they descend towards the surface of the Earth. Okay, and as they descend, they're not stable particles, they decay, okay? They decay. And they travel at a certain speed while decaying. Now, an average muon would decay over a time interval of 2.2 microseconds. Okay? And suppose you know the speed of the muon. Within 2.2 microseconds, even if you travel at very close to the speed of light, you're not going to go very far, right? Because, you know, it's only 2.2 microseconds. In fact, you take 2.2 microseconds multiplied by the speed of light, which is almost the speed of the muon, you'll find that it's going to travel about 660 meters, okay, from here to there. So an average muon, after traveling downwards towards the Earth by 660 meters, it's going to die, okay? It's going to die. So most of the muons will not reach the Earth, the surface of the Earth, because they died. On the other hand, what we found was that a lot of muons did make their way to Earth. And that seemed to be contradictory to this value. But it's not because we measured this value wrong. This value, 2.2 microseconds, is the average lifespan of a muon when we can capture it in our hand, which means it's not moving. So we're measuring the proper time interval between the birth and death of that muon. Okay, proper time because these two events took place at the same location. But in reality, the muon is actually traveling very fast. So it's like a fast-moving space shuttle. When we look at everything, slows down, including the life of that muon. Okay, the life has been dilated, which means the muon appear to live longer. Okay, how much longer? By a factor by. And if you look at gamma using the speed of light, you'll find that the muon can live considerably longer, about by a factor of 2 or 3, and as such, it's going to travel a lot further. Okay, with the same speed, can travel a lot further. It can travel 4.8 times 10, about 4.8 kilometers. So it's more than, the gamma factor is more than 2 or 3. But anyhow, you can calculate that, and the result agrees very well with the experiment. That solves the mystery. How come these muons didn't really die? Okay, because as they travel at high speed, their lives seem to be extended because of the time dilation factor. So with the same speed, they can travel further distance. This experiment has been verified by precise measurement, and in fact, even though time dilation seems to be a very exotic event, which we cannot relate to with real life, in the atomic world, when we look at fast-moving particles, this is the rule of the day. Everybody routinely can travel close to the speed of light, and they can routinely live a lot longer from the stationary lab point of view. So this is nothing special in the atomic world.